So this will be a lecture series on higher dimensional physics, and in this series I'll be going through some of the topics that include compactification and identification, which I'll be going through in this lecture itself. And then I'll talk about the extra dimensions and what is their role in what is called the hierarchy problem in physics, which I'll also discuss in somewhat detail about the hierarchy problem. And moving on, I'll talk about, or we'll be developing the Kaluza-Klein theory and the framework for such a theory. And then I'll also talk about higher dimensional gravity, the general formalism, where I'll be telling you about the decomposition of the Kaluza-Klein states and how do we secure the propagators. From where I'll move on to the coupling of the Kaluza-Klein states to matter itself. For example, coupling of these states, Kaluza-Klein states, to scalar and gauge bosons and to fermions as well. And with that, I'll conclude the series. So this will be the first lecture in this series, where I'll be giving you an idea of what higher dimensional physics is, and then we'll talk about the compactification and identification method in higher dimensional physics. So let's start with the question, what is a higher dimensional physics? Or where do you get the idea of having more than three spatial dimensions, right? So the thought of extra dimensions arose from the attempts to unify the forces in nature. So we know that we have gravity, we have weak interaction, we have strong interaction, and we have electromagnetism. So the idea which was proposed by Nordstrom, he proposed a higher 5-dimensional theory, so in which you have your usual 4 spatial dimensions and you have your time dimensions. So those are your 4 dimensions, and you add another dimension to your theory of vectors to concurrently describe the theory of electromagnetism and scalar gravity, right? So the idea was to somehow combine these two together. Okay, so succeeding the discovery of the theory of general relativity, Kaluza and Klein recognized that Einstein's theory in 5 dimensions, where if you take one spatial dimension being compactified on, where one spatial dimension is compactified on your circle S1, right? So S1 is just a topological language of a circle. So it's a one sphere. And this, let me give you some sort of visualization of what this would look like, right? So let's draw something. Let's draw our axes. Let's say that you have your space, which is your 3 space. Let's call it 3 space, is in this direction. Let's say that your time is along this direction, so this is your time, and you have your extra 5th spatial dimension along this axis, right? So let's call this 5, let's call it 5th dimension. Now the compactification is done like this along this axis, right? So along the 3 space axis. So this is where you have your compactification, and the idea of this S1 here comes from the fact that you have a circle like this, and this is your extra dimension, right? So the idea is that this is how your the extra spatial dimension compactified on S1 looks like, right? So you can think of this as you have your let me just put this in there so it's much more clearer. So let me make it small and let's just put it over here, right? Let's see if this is, well, yeah, so it's something like this, right? So that's the whole idea over here, right? And well, you can also think of it like, let's say that you have, let me just draw this one more time, right? Let's draw this thing again. So this is your S1, and we know that the radius of this circle is, let's say, R, and along this you have your, you could have your x4, right? So you would have your x4 along this circle, while where, note that this 4 is your extra dimension, because in physics we usually use indices from 0, 1, 2, 3, and so on, right? And the rest of those are your, this one along this line, which is your 3 space. So we denote it with x mu, where everything else is along this line, while your x0 is along this axis, which is time, right? So that's your x0. So anyway, I hope you get the idea. We'll discuss this in more depth later on. I'm just starting right now. But the idea, the idea that Kaluza and Klein recognized was that the Einstein's theory in 5 dimensions, with one spatial dimension being compactified on this S1, it can describe not only the 4-dimensional gravity, but also electromagnetism, right? And that's something amazing, right? So what they realized was that you could combine these two forces if you are provided with this extra dimension, right? So, well, during the developments of then the superstring and supergravity theories in the late 1970s, higher dimensional physics picked up stardom, right? So it became very famous, and the reason was that superstring theories required themselves, they needed these extra dimensions, right, for superstring theories to work. So that's why they got the higher dimensional physics became so famous. Now, however, the problem is of the scale of these extra dimensions. So the scale of these extra dimensions is of the order of Planck length, right? Which is written as MPL minus 1, and therefore they are undetectable at our current energies. So with this now, let's move on to the topic of compactification and identification. I'll go to the next page, so we have a clear page over here. Now, well, let's start compactification and identification. So I'll just write compactification, let's not waste time. Now, it is certainly possible for the extra dimensions to be undetected by the low energy experimentation if the dimensions are curled up into a compact space of volume. And these curled dimensions into this compact volume space, there is a name for these, and it's actually called a Calabi-Yau manifold. But obviously more on that later. For now, consider a one-dimensional world. So what that would look like is you would have an infinite line that keeps going on and on in these directions, right? And then you let the coordinates along this line, let's call it x, right? So this is, you can think of it as your x-axis, an infinite x-axis. Now let's do something on this. Let me first draw the figure, and then I'll move on to the explanation. So let's say you have a person standing on this line, and you have the same person like this. Okay, cool. Now let's say that the distance from this, and I said same person, I'll get to that in a bit, right? Let's say the distance from this person to the person on the right is 2 pi r, and again to the left is the same, it's 2 pi r. Now obviously this person would have hands as well, right? So let's just quickly draw those. Anyways, now if you look at this figure, say you pick a point P. For every point P along this line, there exists a unique real number, and I'm going to call that unique real number x of P, right? So this is known as the x coordinate of your point P. Okay, now let me talk something about a fine coordinate, right? So a fine coordinate on your line must always satisfy two conditions, right? And let me write it down. So for a fine coordinate, so if you want to call a coordinate a fine coordinate, it should have any two distinct points that are P1 and P2, and such that these two are not equal, right? So obviously there are two distinct points. They should have different coordinates. What that means is that your x1, or let's just say x of P1, should not be equal to x of P2, right? So that's one of the conditions. The second one is simply that the allocation of your coordinates to points is continuous. So what that means is that the nearby points have practically equal coordinates. So if you have if let's say P1, or let's call it something else now, let's call it P3, is very close to let's say P4, in this case you have x of P3 is equal to x of P4, right? But you should know that these two coordinates should be close to each other. And what this actually means is that the allocation of your coordinates to your points is continuous, right? So that's all this means. Now let's say that if you were to select an origin on this infinite line, right, then you can define a fine coordinate on this infinite line, right? On this infinite line, all you have to do is select an origin of your choice on this line. Because it's an infinite line, you can choose your origin. For example, let's say wherever you're standing on this line, you may call that point your origin, and then you can choose or you can define a fine coordinate on this line. Now, a coordinate allotted to each point is simply the distance from that specific point to the origin, right? So let's say you have let's say you're standing here. You say that this is your origin, and let's say this is your point P, right? So now a coordinate that is allotted to each point is the distance from that point. So it's just the distance from this point to your origin. So it is this distance, right? Okay, now let me just get rid of this example that I just made. Let's keep it an infinite line. Now, for a moment, picture that you live on this rather boring one-dimensional world, but periodically every let's say over here that period is, you can see, 2 pi r. Periodically something weird happens out of nowhere. Every time you walk a certain distance, the scenery simply repeats itself, right? So what that means is that for every 2 pi r distance you move either to the left or to the right, the scenery repeats for some value of r, right? So r can be anything. Now, say if you were to meet your friend, let's call your friend Feynman. Why not, right? Now, you would observe that there are clones of Feynman at distances 2 pi r. If you keep moving along, you would have 4 pi r, right? And then you would have 6 pi r, 8 pi r, and well, so on, right? Now, both this will happen if either you're moving to the right or to the left, right? And it would happen with the same amount of spacing in between, right? Now, so you see, there is absolutely no way in which you will be able to distinguish an infinite line with such a peculiar feature from a circle whose circumference is specified by this 2 pi r, by this period, right? And as a matter of fact, saying that this strange line is actually a circle puts this strange nature into perspective, and that is simply that there are no Feynman clones, but you rather meet the same Feynman multiple times as you move around this circle. Now, mathematically speaking, one may think of a circle as an open line with an identification. Now, that identification is your 2 pi r, right? Let's get into the details of that in a bit. And by the way of explanation, we will declare that points with coordinates that differ by this 2 pi r are actually the same point. So this is actually the same person repeating periodically, right? And so that's why I said that these are the same people and not different people. So in a precise manner, 2 points are said to be the same points if their coordinates differ by an integral multiple of 2 pi r. Now, to write that down mathematically, it is simply to say that these 2 points are same, or they are approximately equal or something like that, if their coordinates, that is x of p1.1, is equal to x of p2, and this thing is simply equal to x of p2 plus some integral multiple of your 2 pi r. So you multiply this 2 pi r with some n, where n is an integer, right? So n belongs to the family of integers, right? Okay, cool. Now this is actually the same as to say that the 2 points are same, which are x is the same as x plus this 2 pi r. And you can read this line as identify any 2 points whose coordinates differ by this 2 pi r. So that is what you mean by identifying 2 points, or an identification. Now with such an identification, the open line really actually becomes a circle, and so the identification has turned a non-compact dimension, where the non-compact dimension is this infinite line which goes on forever and ever. It has turned, the identification has turned it into a compact dimension, right? Where that is a circle, right? So now here you must note that your interval, which is defined by this thing, that x lies between 0 and including 0 and 2 pi r, this interval is your fundamental domain for identification. Okay, now let's move on to this topic of compact dimension, or compactification, right? We have compactified our infinite line into a circle. So let's talk about this compactification. First of all, well, the trouble with compactification is that one cannot impose it blindly on whichever dimensions he likes. That's not possible. The combination of the macroscopic 4-dimensional space-time plus the compactified extra-dimensional space must be a solution of the higher dimensional Einstein's field equations, right? So let me repeat this. You cannot impose the idea of compactification on how many dimensions you might want to, but what must be true is that the combination of macroscopic 4-dimensional space-time that you can see, right, where you have 3 spatial and 1 time, and you add the compactified extra-dimensional space, now this whole thing together must be a solution of higher dimensional Einstein's field equations. In other words, one must be able to recover the ground state solution that consists of 4-dimensional Minkowski spacetime plus another d-dimensional compact manifold. You can see that this is pretty straightforward when you're working with d is equal to 1, and that is the Klein's case. But the same thing cannot be said about even higher dimensional theories where compact spaces are rather curved. So one example would be of the Calbi-Yau manifold. But moving on from here, I'll be talking about the Kaluza-Klein theory. I'll tell you about the hierarchy problem and why do we need extra dimensions, or what does extra dimensions in that particular problem mean, right? What would they do? How would the extra dimensions help? Uh, so well, let me just before ending this lecture, let me just give you an idea of the hierarchy problem. One way of looking at the problem is that, well, you have your forces, right? If you come back here, you have these four forces. The problem is, or one way of looking at the problem is, why does gravity appear so weak compared to electromagnetism? I'm not sure, but I think the number is one with, I think, 40 zeros next to it. So I think it's like something about 10 raised to power 40. It's a very large number. And so gravity is so weak. To give you an idea, just think about the fact that if you pick up a magnet, a small magnet, a very tiny magnet indeed, and you just go and put it on your fridge, for example. Now, think of this situation as where the entire Earth, which is so massive, the entire Earth's gravity is pushing that magnet down to itself, right? Because I use the word pushing because gravity is rather the curvature of space time, right? So the entire Earth's gravity wants to bring that magnet down, but it does not fall, right? It sticks to the fridge firmly and pretty strongly, in fact. And that gives you an idea of how weak gravity is when it is compared with electromagnetism. And so that is the hierarchy problem. And I'll also give you a bit of a hint of how does extra dimensions solve or claim to solve this problem, right? So we say that you have, let's go back and take this diagram. So I'll just draw it again over here. You have your 5 dimension along this line, and you have your time along this, and your usual 3 space along this, right? So let's call this extra dimension. Now what happens is, or what we say that happens is that gravity is actually pretty strong. But what happens is that the flux of gravity, it does not only go into this 3 space. What happens is that it also, the gravity also dilutes into these extra dimensions, and therefore it loses its flux. Well, this is a pretty rough diagram, right? But it loses its flux, and only small amount of gravity appears in this 3 space dimensions, right? Where most of it is lost in those extra dimensions. And therefore gravity appears as though if it were very weak compared with the other forces of nature. But extra dimensions is saying that it only appears weak because the flux of the gravity dilutes into those extra dimensions as well. Now, there is a whole topic devoted to this, where you need to understand the concept of D-branes, thanks to Joseph Pachowski. I hope that's how you pronounce his name. But he invented the concept of branes, which allowed us to model this and obviously more, but this situation in the form of branes where, well, I'm getting ahead of myself. we'll talk about that in the upcoming videos. Let's stop this one for now. See you in the next video.